All right, today we're showing off our stochastic multiplier that just came back from Tiny Tape Out 5. Here's the demo board. And we've done a few tests. And so a stochastic multiplier uses a simple digital gate called an AND gate to multiply two signals via probability. How do we do that? Well, we'll take a binary weighted digit, convert that to a randomly generated series of digits. For example, if I have the number 1 on a 2-bit number, I need 4 clock cycles to show that 1. But that, as long as there's 1 1 every 4, it doesn't matter which position, right? I have a probability of a 1 being a 4th. And so then if I have another signal that is also a 1 out of a 2-bit signal, which means 4 time slots, so 1 1 anywhere it happens in 4 clock cycles would be another 1/4. So the AND gate will multiply that by together just by taking the AND of the function, and you'll see on average you'll get 1/4 times 1/4 is 1/16. So every 16 clock cycles, somewhere in that bit stream, you should only see 1 1. Now what we've got here is in green, we're encoding the number 3, and in blue, we're encoding the number 3, right? And so that means there's 3 1s every 4. They don't have to be in the same position, right? But on average, there'll be 3 1s every 4 clock cycles. And then the ANDing, you can just look, right? If everything has to be 1 to be a 1, right? And you can freeze that and look at it. But to test it, I don't have to count the number of 1s in purple. I can just take the average. So the average of the line in purple, which is 3 times 3, which turned into probabilities, is 3/4 times 3/4, which is 9/16, right? The answer should be 0.56, and what we're getting is 1.67 divided by the power supply voltage 3.3, and so we're getting about 0.54, right? So it's actually working, and it's relatively easy to test, and that average is actually how long you're on. So if I was connecting these signals to an LED, right, the green and the purple signals would be on 3/4 of the time, and so they would be brighter than the purple signal, which is on 9/16 of the time. And this is actually can be used to drive things like power LEDs and motors to get rid of the higher harmonics. So if I turn on the FFT, right now it's on the clock, and you can see these big harmonics, right? So that noise can actually cause, noise that you can hear. But now if I start looking at the encoding of the pseudo-random signal, that's A and that's B. They're different, right? But notice the shapes are the same. And then C, the multiplication of them all, right, gives you that. Now really you have to look at the A0 constant of the FFT, the DC average, to get it to work. But you can see that using this as a kind of pseudo-random PWM, you're spreading that energy of those harmonics, which are hard to filter out, making it broad. But you can see that all you're doing is taking the average of 1s, and you could just think of it in terms of the clock is like well, the clock isn't random, excuse me, but you're taking a coin and you're flipping it, and A and B, the inputs, right, they're kind of a weighted coin, so that 3/4 of the time you get heads, and 1/4 of the time you get tails. And then when you take the anding of it, which really both have to be on to get on. If anything is low, you get low. So this could be a great workforce development introduction to circuit design. Because you don't really need calculus, and actually it's kind of just based on statistics. So even though calculus is buried in there somewhere, it could be a great intro. Anyway, I'd like to thank the team mentioned in the chat, mentioned in the post. But great job, everyone.